Today's lesson is on conditional probability and independent events. First, we're going to talk about what conditional probability is. The probability that E, given that F occurs, is called conditional probability and is denoted P of E given F, and that's exactly how you pronounce it. So the probability of event E given F occurs is found by the following formula. So P of E given F is equal to the number of E and F, that's intersection F, divided by the number of F, where F doesn't equal 0. Or you can think of it as the probability of E and F, or E intersect F, divided by the probability of F. Either way, if you want to think about a number of or probability, it's the same thing. So for example, suppose you roll a 6-sided die. Find the probability of rolling a 3, given that the outcome is a number less than 5. So your friend rolls a die and takes a look at it and says, okay, I'm going to tell you that it's less than a 5. Now what's the probability of rolling a 3? So they gave you some information about the die, but you still have to figure out what the probability is. I know it doesn't make so much sense with someone hiding the information about a die, but it's going to make a whole lot more sense in our future examples that are a little bit more complicated. So we decided to start with a simple one. So what are the number of ways that we could have a number less than 5 and a 3? Well, there's only one way you can have a number less than 5 and it being a 3. What's the number of less than 5? Well, there's 4. And the reason it's 4 is because 1, 2, 3, and 4. We can't include 5 because it says less than 5, not less than or equal to 5. So what's the probability of rolling a 3 given that is less than 5? So that is 1 out of 4. Therefore, the probability of rolling a 3 given that a number is less than 5 is 1/4. So let's give another example here. Suppose you're dealt one card from a 52 card deck. Find the probability of getting a 9, given the fact that the card that you dealt was black. So you know it's black, but what's the probability of getting a 9? So let's see. We have the number of 9 and black is 2. There is the 9 of clubs and the 9 of spades that are both black. How about the number of black cards total in the deck? Well, that's 26. So the probability of getting a 9, given that it's black, is going to be 2 out of 26, which is 1/13. So if you get the information that it's not red, then it takes all of those red choices out of the mix, and you're just trying to find the probability of a 9 out of the black cards. Next, we're going to use a table with some probabilities of a U.S. woman aged 49 of positive mammogram versus negative mammogram, and then whether they actually have breast cancer or no breast cancer. For those of you who don't know, mammograms usually detect breast cancer in women. So we're going to let C equal cancer and M equal a positive mammogram. So if there's no breast cancer, that's going to be C prime or C complement, and if it's a negative mammogram, then it's going to be M complement or M prime. For part A, what is the probability that a patient has a positive mammogram given that she does have breast cancer? So the fact that we know she has breast cancer means I'm going to only look in the breast cancer column, and all of the other columns I'm not going to even worry about. I'm looking for the probability that she has a positive mammogram, that's M, given that she has cancer. So when I'm looking for these, I'm looking for M intersect C. So M intersect C is where she has a positive mammogram and breast cancer, that's 720. Next, I'm looking for the total number of cancer, which is going to be 800. So what's the probability that she has a positive mammogram given the fact that she has cancer is going to be 720 divided by 800. I can divide by 10 to get 72 over 80, and then divide by 8 to get 9 over 10. So 9/10 is the probability that she has a positive mammogram given that she has breast cancer. Next, we're looking for the probability that she has breast cancer given that she has a positive mammogram. So this is just backwards. So probability that she has cancer given she has a positive mammogram. So I'm going to erase my yellow highlight, and I'm going to highlight just my positive mammogram because we know she has a positive mammogram. We know it. Okay, so now I'm looking for the number of cancer and mammogram, which is the same 720 from before, and I also need the number of positive mammograms, which in this case is 7,664. So we have 720 over 7,664. I can divide the top by 8 and the bottom by 8, and that gives me 90 over 958. Use a calculator if you need to. I think that's at least divisible by 2 again. So this is 45 over 479. For this fraction, you might want to consider using a decimal. So that's going to be 0.094 if you use a calculator. For the part A, it was 0.9 if you wanted to use a calculator. Part C says to find and interpret the probability of C complement given M. So what does that mean? Well, what we're looking for, what's the probability that she does not have cancer given that she has a positive mammogram? So given that we have a positive mammogram, we're still talking about that same M positive mammogram column. So the probability of C complement given M is equal to the number of C complement and M over the number of M. Now, we've already looked at the number of M. We know that's 7,664. What's the number of the C complement and M? So not cancer and a positive mammogram is 6,944. If I divide the top and the bottom by 16, I'm getting 434 over 479. And if I divide that out, I'm getting 0.906. So let's interpret what this means. This is the probability that she does not have cancer given that she has a positive mammogram. So just because she has a positive mammogram doesn't mean she's necessarily going to have cancer. There's actually a pretty good chance that she might not. There might be some other irregularities on her mammogram that might have been causing the positive mammogram.